Okay, so continuing off from our NRTL problem, if you remember last time, we coded out a function so we could solve for that gamma, and that was we needed to input parameters for a known liquid composition and temperature. So on to the next part of that, we're going to be plotting the binary XY diagrams and also, in our case, a temperature XY diagram. And the reason why we're using temperature, if you remember when we did bubble T, bubble P, the bubble pressure, bubble temperature, as well as dew temperature and dew pressure, those were all just ways we could calculate equilibrium given a composition of um, well, X or Y, liquid mole fractions or vapor mole fractions. And obviously, depending on whether that's bubble or dew, we're looking for the first bubble or the first dew. And again, with temperature or pressure, given the other one that's missing, essentially. So again, in our case, the reason why we're using temperature, um, well, I guess bubble temperature in this case, we'll need to code that out as well. So we include the gamma function, not just use at the very beginning in a previous video, we did bubble temperature, but we use an ideal case with Raoult's law. But in this case, we have I wouldn't say corrected, but Raoult's law for including non-ideal mixtures with including that gamma activity coefficient. It goes something like the liquid mole fraction times the gamma coefficient for that particular component times its saturation vapor pressure. Then, of course, the same right-hand side of the vapor mole fraction times the total pressure. And obviously that was also always equal to partial pressure. So now we have to include this gamma variable within our expression for solving for equilibrium. And as you know, with at least the bubble calculations, this is our first bubble, and we're given a known liquid composition. So we're given an X, and essentially, depending on whether it's temperature or pressure, obviously we'll put temperature or pressure here. But in our case, if we have bubble temperature, we'll be needing to put pressure as a parameter to solve for. And of course, to get that pressure to solve, we'll need to do, again, we've done this before. It was with our first bubble dew graphs where we created the bubble pressure, and then to calculate the bubble temperature, we use a root to essentially find the difference between our guess of our bubble pressure minus the pressure we actually want to be at. Oh, I'm sorry, I don't know why I put temperature there. It should be a pressure. Um, so between that, our bubble pressure function and this pressure until it equals 0. So we set them, subtracting them from one another, and then using a root to find the 0. And we just use the root function. And today we're going to be using a root scalar. It's very similar to the root function, and I actually have some tabs pulled up on Chrome for that, but kind of getting ahead of myself. But again, we're using bubble T since we need to have this liquid mole fraction that's included in our gamma function. And you'll see that in the code we wrote before, where this gamma function is taking a liquid mole fraction. So it just simplifies things if we already have a liquid mole fraction. And then I guess the other reason you would use bubble temperature in this case, well, we have constant pressure, and constant pressure is obviously one of the more likely of the 4 different types we can use: bubble temperature, bubble pressure, or dew temperature, dew pressure. At least with the two temperatures, bubble temperature and dew temperature, while those are both at constant pressure, well, we choose constant pressure since it relates more closely to a distillation column, but I already explained why we chose bubble temperature. So again, we chose it because we have a known liquid molar fraction we're inputting right there. Okay. And then I have some notes for myself. I think in the last time we did an isopropanol-water mixture, so I just made a note to, we're doing this for ethanol water in this case, I believe. Or no, it is isopropanol-water. Okay, never mind. I guess the examples are different, but I guess I don't need to change it then if it's already isopropanol. So let's get rid of that. And we can go ahead and look up that isopropanol water. Yeah, and it's only this one part actually. So yeah, I made a note for the wrong mixture, so we also don't need that, I guess. So I guess we'll just look those up as we go. So let's switch over to our code, and I can kind of talk more about the root scalar and why we did that. So I kind of just Googled this, but according to the Google AI, supposedly, and it makes sense, with SciPy root that we used before, it's for multivariable functions, solves a system of equations, but with our root scalar that we're using today, again, it only just solves one variable input. So it's actually the more, I guess, related case that we're going to be using, since we've only ever used the root for one variable. Oh, that's not true. Or no, I'm confusing it with solve IVP. But anyways, that's that. And I guess we should also pull up the isopropanol-water, since that's what we actually want. So again, we do by mole fraction, since that's what we're graphing. But looks like it is 0.68. So that's the number we'll have to look out for. And then you see it is different by mass percent. So you can graph mass percent on the bottom. I think I've seen volume percent too. But in our case, we'll do mole percent, and I believe of its IPA. So yeah, this is our thing. I think it's been over a week since we went back and did it. So let's just run this all again. Um, got too many practice sessions up. So that and run it all. While that's running, again, going back to our root scalar and roots, and I also have the chemospline. I can't remember if I did this before in a previous video. I think I did it with constant relative volatility, but more on that later. Focusing on the root scalar and root, the only major differences are with root scalar, like with root, you can provide an initial guess, but you need to specify a method for that. And the methods are down here. So if you supply an initial guess, so X is required, and then a 0 or an O is optional. And I believe we can use secant here. So we just provide one initial guess. And we don't need a bracket for that. So that's what we'll be doing for the most part. We'll go back and use this as well to actually calculate or identify this value of the azeotrope. So the azeotrope is when the y1 and x1s are equal to each other, the vapor mole fractions and the liquid mole fractions. So we'll find that value when the two lines intersect on our binary xy diagram. But yeah, we'll use root scalar for that. Essentially finding the zero between the difference of the y1 and the x1, the vapor mole fraction and liquid mole fraction. But if we don't use this initial guess parameter with root scalar, you actually don't have to provide anything else. You can provide a bracket, if I can find it right here. So it's just a bracket, kind of a range where we expect the root to be. So obviously we want to input a correct range. So we can use both methods. Honestly, I might just use the initial guess for within our bubble temperature function, and then when we identify the intersection for our azeotrope mole fraction, I can do the bracket here. So yeah, and then this Akima interpolator is another way we could get that intersection, but we'll leave that for now. I think we can get rid of root for now. Yeah, so this ran perfect. So what do we want to do? We're gonna be creating our we need a way to get our equilibrium points. So that's with let me put away my iPad. So that's with our, again, we decided on using bubble pressure and temperature. So that's what we'll do since we have a given liquid mole fraction. So I'll start with the bubble pressure, since that's what we need to end up using in our bubble temperature. So go ahead and define that. Define our bubble pressure NRTL. Again, specifying, since we did ideal in the previous scenario. So bubble pressure, again, we take a liquid mole fraction and we take a known temperature. So I hope I have those defined already up here. So we have a temperature. I don't think we have a pressure. So go ahead and do that. I think we already have a, yeah, so we have an array for our mole fractions of isopropanol-water. Yeah, let's define our temperature. I don't know, something like 373. And what we can end up doing as well is when we actually have our bubble temperature, we can kind of use the bubble pressure and temperature to check each other and make sure they're working the same. And what I mean by that is when we input a temperature given by our bubble temperature, it should output the pressure that we will input into our bubble temperature. So at least, yeah, hopefully I said that right. But I'll do it again and say it again if I said it wrong. So yeah, we have an input, liquid mole fraction, and a temperature. And what do we want to do? Well, we have Raoult's law. I'll go ahead and write that down with our gamma. I think I have oh yeah, here's what I was talking about earlier. Remember, our gamma was taking in a liquid mole fraction and temperature. So that's why it kind of works out pretty easily when we use our bubble pressure and bubble temperature, since we're already inputting that liquid mole fraction. If due pressure and due temperature, it'd be a little bit harder since we need to have some sort of guess for that liquid mole fraction. And we do that using the ideal forms of them, but to keep things simple, we'll use it like this. So we have gamma, I don't know, gamma I'll just say that. And then saturation vapor pressure times the mole fraction, vapor mole fraction, total pressure, and that's our partial pressure. So, I mean, we have our X, we have our T, so that's our liquid mole fraction. We know our gamma since we know our liquid mole fraction, and we know our saturation vapor pressure since we have a temperature. And what are we solving for? We're solving for this pressure. So an easy way we can do that is we just solve for the partial pressures, and then we'll take a sum of those, and that'll just be our liquid mole fraction. So I'll go something like partial P is equal to, well, pretty much this. Well, I'll go ahead and type it out. So X times, we have our gamma function, and that takes, I believe it's just liquid mole fraction and temperature. Yeah. And then we have times our vapor pressures at a temperature. That's the input temperature we have up here. Kelvins there. So that's our partial pressures, and if you have all the partial pressures, then all you have to do is sum those up. I go something like MP sum of those partial pressures. And honestly, we could already just return these as, since we have our pressure, and then I could do for Y, that would just be partial pressure over pressure, but I like to show where it's coming from. So that's just me. I mean, it's just one extra line of code, but pretty sure we want to limit those if you're kind of a more experienced coder, which I am not. So again, for just my learning purposes, I divide them and then I'll display it there. So let's go ahead and see if this works. Awesome. And then we go ahead and just call this since we already have our parameters defined. Okay, so it works. So this is our liquid mole our vapor mole fractions, and then this is our pressure. I believe we're solving for 101,325 pascals. So let me go ahead and double check on the iPad here. Yeah, 101,325 pascals. So perfect. That's what we'll be inputting once we define our bubble temperature. So do I have it defined up here? I don't. Oh, but I already have a temperature too. Okay, whatever. Why not? We can just keep it all here. Redefine it all. So this is in pascals. Yeah, if that's working, we can just keep it as like that. We can kind of actually just kind of guess where this would be. So if this is too high, I'll maybe go a little lower since it's about double what we have. Maybe like 320. Oh, this is 28,000. That's my bad. So we actually need to go a lot higher if we want 101,325 pascals or 1 atmosphere, maybe like 370. Now we're too high. Okay. I won't try to beat the system. I'm not a good root scaler anyway. So yeah, let's actually make the function instead of me trying to do it myself. So we have our bubble temperature, NRTL. We still take a liquid mole fraction, but this time we input a pressure. So So what do we want from this? Essentially, we're returning a temperature and then again the vapor mole fraction. So if we return a vapor mole fraction, honestly, we're just copying this line of code here. So I can just copy that down. But we are given the pressure up here, so we actually don't need to calculate it. So I can just complete that line. And then now all we're missing is this temperature. So we need a temperature somehow. I'll go ahead and comment that out. The way we get our temperature, that's right, we use we iterate between our bubble pressure and our pressure that we want. And this is where we use the root scalar. So we're going to be finding the difference between the two. That's what the root scalar does. It finds the zero of the function. So define a function that is essentially returning the zero, or at least the difference between these two. And yeah, I mean, that's pretty much it. And then we set t to whatever attribute of root scalar that gives us that temperature. And I think we'll want to do that as a result. So the best way to do this, maybe we could do it outside for a little bit. So we do like find a function, p like guess, or p deviation, maybe p difference. So that will just take, well, let's see what it takes. What we want to do is, again, we're subtracting the difference between the two, so I can just go ahead and copy this down, honestly. So we're calling this function, supplying it with our liquid mole fraction, which is actually already supplied here, so we should supply a temperature to this function. Yeah, that makes sense since the root is finding the temperature that satisfies this expression that I'm typing. So it's the difference between these two, but we also should remember with our function here of bubble pressure, we're outputting two different outputs. We have our pressure and our liquid mole fractions. So we just want our pressure in this case. So I believe we just need to do a 0 there. Hopefully that works. And then we can try doing our, let's just hit Shift Enter to see. Awesome. Okay. And then we can do our root scalar of that. So root scalar, I don't think I imported anything. Yep. So let's go ahead and import all our things we need. So we'll need from SciPy, is it optimize? We import our root scalar. And then from Plotly to graph our plots, we'll do subplots, import, make subplots. All right, did that correct. So we do supply our function. Well, let's just look. Root scalar, we supply our function, and then that's right, we had the two different methods I was saying. So I think I said I wanted to do an initial guess for in our function about the brackets. So I mean, yeah, we could just do that. So if we have a initial guess, that's x0, which is required for secant, and we don't want brackets, so that's what we want. And then an optional second guess there. So we'll do method is equal to secant. So we supply our function first, so that's our pdiff. Then we supply our initial guess of something maybe like 373. And then we do method is equal to secant. Let's see if that works. P is not defined. Did I not hit Shift Enter here? I did not. Okay, so looks like it converged. Awesome. So it looks like this root attribute is giving us our temperature that we desire. So that's what we'll set our temperature to. So something like temperature is equal to, make it a different one since it's taking T from another place. And then we do maybe the root of that. And we should display it. So yeah, that's what we'll do. I'm debating whether or not I want to see the result, or I can just do it straight like that. Yeah, I might just do it straight like that. So I mean, I might just, well, copy and paste this in. But that's right here. Shift everything over, control bracket. Yeah. So we should get that same 354 if we do everything correct here. So let's go ahead and call our function. Shift enter. Awesome. Shift enter. There we go. Not too bad. Okay. So we got our 354, and then we have our vapor vapor mole fraction. So what I was saying earlier when I said we could check our two different values, our two functions, we got a temperature outputted from our bubble temperature. So we want to plug this temperature into here, and let's see if this gives us the same pressure of 101,325. Awesome. So again, this 101,325 is what's being put into this pressure. It was right up there. So just a little check to make sure you did everything right, or at least I did everything right. So yeah, now we have our pairs we can get. So we have our vapor mole fractions that we can get from a given x. So if we want to graph a full I guess plot of our xy's or xy diagram, and then our bubble T are at constant pressure, then we'll just use this bubble temperature function essentially. So if we want to graph not just for our x's, our liquid compositions given up here, but for a whole range covering the entire fractions of 0 to 1, then I can create a new I guess a new array of those values. So maybe something like x1s is equal to np lin space. So again, evenly spaced points between 0 and 1. I don't think that we need to make these floats. And then I'll do, since I want to include 1, I'll do 101 points. It shouldn't really make a difference if I make it bigger now. It might just take longer to run, but we'll see. Well, let's make it small. Why not? The reason, I think I already explained it, but the reason why we're doing 11 points here is so I have a point at 1. So, I mean, we can just look at it, honestly. Yeah, we include 1 there. So if I didn't include 11, we'd have 1, 2, 3. So again, all the way up to 10. So this would just be 10 versus, I mean, it should say 11. Yep. Okay. Anyways, so we have our x's, and then we want to plug this into our bubble temperature to get an outputted temperature. That's what we're graphing. But then we also have our y's. So honestly, we can unpack that. I think this is a so we could actually loop this. I think we'll be looping all our x1s through our bubble temperature, and then we can unpack all those values as they come and then plot them. And we should store them as lists too. So yeah, let's do that. So we want to do so for x1 and x1s, maybe we do our bubble temperature. We just call that here. So we have this. We're iterating through our oh, I see. So for again, this a little confusing here. So X is a composition of both our components of isopropanol and water, and here I only generated components for one of those mixtures. So something I could do is, I wonder, I don't know if I want to define it this way. Yeah, we'll just put it inside. So we'll need to make something similar to X. So X was essentially this right here. So I'll go ahead and copy this, but we need to format it the same way as we would if all of these were, so one of these is our isopropanol and the other one is our water. So one of these, I think it'd be easier if we make this isopropanol. So we do something like our x1s. So now we're doing a wider, pretty much the entire span of 0 to 1. And then to get the other side of that, essentially, since it's out of 1, we just subtract it from 1. So 1 minus that. And I wonder if this would work if I put it in like that. Maybe I call it some other value. What do you want to call that? Total total composition, maybe total x total makes sense. Kind of, I'm not good at making names, so hopefully that works if we do that. So actually, I want to see what that looks like actually. So total. Oh, yeah, we actually got our points. So yeah, so now instead of just the, what was it, 0.6 and 0.4, 0.4 and 0.6. So the first array we can call it isopropanol. The second one is water. So instead of just these 2 points, now we have all the points supplied for each side. So that should work. Go ahead and do that. All right. So what do we get from doing this? Yeah, I don't think this is actually going to work since we need to do a loop through all of them. So actually, it was a good idea, but I think what we actually want to do is we'll still have an array to supply it since we do want different compositions, but it should be based on our loop. So that's my bad. Yeah. What else do we want to do? Do we want to see what this looks like maybe? Maybe something like want to see what it looks like. Oh, I need to unpack this since it's multiple variables. Maybe I could just unpack it here, honestly, since we're outputting our temperature and our two y's. So let's just unpack it, honestly. So we have our temperature, and I think we can do a maybe like a nested tuple. So y1 and y2. See if that works. Will it yell at me? Do I need a comma here? I already have a comma. Let me just run it all. Oh, okay, it works. I don't know why running it all just fixes that. Okay, so we should be iterating for all of those. So let me check that. We only want y1. So okay, so we have a temperature. I guess it just runs through all of them. So if I did like 1, oh, I need a supply. So 1, 0. Is it worth checking? Sure. I'm just checking what it is, seeing if it went all the way to the end. So it's like 1 to 0. Yeah, that did go to the end. Awesome. And it is 1. Okay, so it ran all the way to end. That's why it's giving me this value. So I want to capture all those values. Oh, that's right. I was saying we were putting these in lists. So let's make our lists of temperatures and our list of y1s. And all we have to do is just append them in the loop as they're going. So, man, when you think about it, it's just very simple. So you append our t and you append our y1s. So let's take a look at those. Awesome. Okay. Oh, it's empty. Oh, not y1s, just y1. Okay. There we go. So we got points we can plot. I think we just plot this up now. Did I import subplots? Okay, so okay, we're recording. So fig1 is equal to make subplots, and we're gonna do 2 plots. So one row is equal to 1, columns is equal to 2. So one of them on the left will be at row 1, column 1. That's our bubble temperature. our xy's on the x-axis, and then the xy diagram, obviously x on the x, y on the y, or yeah, the binary xy on. I think we just add, honestly, we add our scatters, add our points. So on the x, I said we have our x1s, and then y is T's, or temperatures, and then we can do a row is equal to 1, column is equal to 1. I think that's it. So that's our liquid mole fractions for bubble temperature. I mean, technically it's constant pressure. Well, I'll just say it's for temperature. How about that? For temp. And then we do the exact same thing, but now we put also our y1s for the second line. And this is our y1s for temperature. Let's check it for now, but I also want to update the layout first, since I don't want to be blinded. Width 1000, height 400, and then show legend false. What am I thinking of? Oh yeah, template. Like I was forgetting something. Slightly dark. That. Awesome. So it looks like we need more points, and these should be lines as mode equals lines. This is the boring part now, just graphing it all up, honestly. Try that. And then we should add more points since it does look like it's working. Should be I could add them later, honestly. You can still see that. Awesome. So I'm just gonna go ahead, honestly, copy paste these down. So one of these will be our x and y's. So I know like maybe like binary xy. And then the other one, we need our 45-degree line for that binary xy. So start here. Honestly, we just make this y1s. And then the other one is list a tuple of our points. So we want to go 0 and 1. And copy paste that. So we have 0, 0 and 1, 1 for our xy. And I need to make them, I just realized, on the second column. Awesome. Let's make this a little like that. That too scrunched? Oh, that's perfect. Yeah, we can, I mean, we can add more points, honestly. I don't like this. It's just pointed and angular, so we can jack this up a little bit. Awesome, we got actual curves. That's what we like. So looks like what are we looking for? The azeotrope. So it says 0.68 for the isopropanol. So around 0.68. Yeah, it looks like that's where it intersects pretty well. Oh, I guess 0.67 here. So pretty close. Honestly, 67.5. Within a tenth of a mole fraction. Even though, well, actually a hundredth of a mole fraction is pretty as close as we're gonna get. So I said we were going to, well, at this point, I guess I should say we're pretty much done. So yeah, this is what it looks like after we plot it up. Again, azeotrope crosses the 45-degree line. That's when they're equal to each other. And then we have a different line for our bubble temperatures. Not exactly a perfect curve as we would have imagined it with ideal mixtures. But now is what I was saying earlier about the intersection. So there's two ways we can do this. Again, root scalar and the Akima interpolator. Let's just start with the interpolator, honestly. So we need to import that. Is that also optimized? It's interpolate. So can I copy this? Be awesome. Not that. So with you remember with Akima spline, we need to take in arrays of x and y's, and then it will interpolate values based on those data points. So once I import this in, like that worked, and then I'll do something like our y1 spline is well, our schema 1D interpolator, awesome, and then we use that based on our x1s and our y1s, which we already plotted up. So I mean, those are equilibrium pairs, so no need to generate any more if we already have the data. And then we can kind of check this if we plug in something, I don't know. Let's see what we had here. So the same temperature, let's plug in something we can find out. So 355 give us 1 and 0, so it should give us 0 and 1 if we plug in well, I mean that's kind of obvious, 0 and 1. Maybe something less obvious, like, so this is 0.5 of our bubble pressure. We're outputted vapor mole fractions. So if I find the liquid mole fractions associated with this, I think it's 0.6 and 0.4. Let's try it. See if I know what I'm talking about. 0.6? Is that 0.6? What am I thinking of? I'm trying to find the equilibrium pair of 0.6 liquid mole fraction. Oh. I think I'm just interpreting this wrong. If I can't figure it out here shortly, or is it 0.4? I'm sorry. Looking at the wrong thing. No, it's 0.5. So when I input an x, oh, here we go. Is it this one? Yeah, okay. So that's what I was trying to find. So we had to input our liquid mole fraction of, for isopropanol, in this case, of the Y1 more volatile component. We input a liquid mole fraction, an x1 of 0.4, and then we get a vapor mole fraction of 0.5. So input 0.4, get 0.5. So that's what I was trying to explain there. So now we have our spline. Honestly, we just use our root scalar. And I think I said instead of using the method secant, I want to use brackets. So with brackets, we just specify the range it could be in. So we could specify all the way from 0 to 1, but we need to make sure we're not stopping at 0 to 1. So what we can do instead is add a little to 0 and subtract a little from 1 so that we don't stop on those bounds. Exactly. So how do we want to do this? I think we use our, we can use our lambda function instead of just defining a function for this. So we're going to take the root of an expression, or of a function, our lambda function, using our spline. So something like lambda of, so we input x1, and then we find the difference between our y1 spline of that x1 and our x1. I think that's right, since we want the y and the x to be equal to each other. Okay, so you subtract them, make them equal to 0. So the root scalar is zeroing that out. And then instead of doing initial guess, I wanted to do a bracket. So we could do bracket is equal to, and then have a tuple of our lower range. I said we're going to add a little to 0. So I mean, I can just put a very small number in the front. So that's 1e to negative 12. Then I'll subtract 1e to negative 12 from the top. So let's see if that works. Should get us that 0.68 value. Oh, not bad, 0.66. Pretty close. Is that actually where it intersects? Yeah. 0.67, 0.66. So 0.67, yeah. Maybe that's it. That's with the spline, and then now I said we were going to do what were we gonna do? Using our actual bubble temperature. So again, this is an interpolation based on our data that we had. We calculated from up here. We use our generate x1s and use bubble temperature to get the equilibrium for the vapor mole fraction. So we can just do this again, but for our expression of bubble temperature right here. But what we do have to remember is that bubble temperature is outputting, again, these two values. So if we want to subtract, if we want to get our vapor mole fraction of the more volatile component, we have to input, so it would be the second output. So we, again, indexing starts from 0. So we do 0, 1, and then we do another bracket to get the first element since this is the more volatile component. So it'd be 1 and then 0 for the first element. So I think I already copied it, so I just replace that. And then we do the brackets. So I said it was the second output, so first element, and then the first output. So hopefully that works. Be the exact same thing, or not. Very different. I put the first, so it should be 0. I don't know why I put 0. 1 would be our water. So 0 is our isopropanol. Yeah, not too bad. So again, this should be a lot closer since it's actually using our equilibrium points versus this is just our interpolation. But I mean, you can pretty much see that they're nearly identical, almost down to like, what is this, the 6th digit behind the decimal point right there. So yeah, those are our two ways you could find the intersection. So yeah, we said 0.6. So yeah. Let's go back to our word problem here. Make sure we did everything. I mean, there's only one part, but so we used our NRTL with this new Raoult's, including the gamma coefficient, the activity coefficient, and we just coded for isopropanol-water at 101.325, and then found the azeotrope location at 0.6 mole fraction, I believe, of isopropanol. So that's what our intersections are telling us, and Google tells us it's also around 0.6. 0.68, 0.67, pretty close. All right, that's where I'll leave off right here. Thanks for watching.